Hey, how's it going? And welcome back to another spicy episode of Bo Maths. Thanks for joining me today. In the last videos, we were discussing what prime and composite numbers, and we saw that prime numbers are kind of like these indivisible numbers where they're not divisible by any number other than 1 or themselves. For example, 7 is prime since the only factors of 7 are 1 and 7. Every number, of course, has 1 and itself as a factor, so that's nothing special, but what's special about primes is that those are the only factors of the prime number. All right, so with this in mind, we are going to really talk about what's so special about prime numbers today. So if I gave you a number, let's say I said 36, and I asked you to factor it, all right, we could go and look at its factors. So we know that 1 and 36 are factors, 2 and 18 are, 3 we'll know is a factor since 3 times 12 is 36, or if we add up the digits of 36, we get 3 plus 6, which is 9, which is a multiple of 3, which means we know that 36 is divisible by 3. Either way though, 3 times 12 gives us 36. Let's see if 4 goes into 36. Well, you know your multiplication tables, you know that 4 times 9 is 36. How about 5? Well, 36 doesn't end in a 5 or a 0, so that means it can't be divisible by 5. And 6 will work because we know 6 times 6 is 36. And as I kind of discussed as a little trick with these are going to be in increasing order, these are going to be in decreasing order, so we know that we've already gone through all the factors because we've reached a commonality here, right? Once we keep going, the next factor will be 9, but we already have that, right? So we're good to go. Now let me go ahead and just pick a pair, let's say 3 and 12. So 3 and 12 are a pair because 36 equals 3 times 12. All right, we know this. But now what I'm going to do is I'm going to say, all right, well, let's consider the factors of 12. The factors of 12 are 1 and 12, 2 and 6, as well as 3 and 4. And you can go ahead and check all of these for yourself and see if there's any others, but there won't be. So these are the factors of 12. So what I'm going to do now is I'm going to replace this 12 with another group of factors. Let's go with 3 and 4. So if I do that, 12 is going to be split up into 3 times 4. So 36 equals 3 times 3 times 4 because 36 equals 3 times 12, right? So these are the same expression. All right, now I'm going to go even further. What are the factors of 4? Well, we know that 1 and 4 are factors, and we know that 2 and 2. So what I'm going to do is I'm going to take 4 and I'm going to split that up into 2 times 2, and I'm going to keep my 3 times 3 remaining. So this will also equal 36. But what I've done here is I've done something pretty interesting where I've taken 36 and I've split it up into 4 numbers that multiply to give me 36. But what do we notice about these numbers? These numbers are all prime numbers. Okay, so let's try this again, but with like a different set of factors for 36. So let's try 4 and 9. All right, so if I take 4 and 9, I can split up 4 like I did before into 2 times 2. And we get this. And then I can also take 9, and what can I split that up into? Well, the factors of 9 are 1 and 9, as well as 3 times 3. So I could split 9 up into 3 times 3, and we get the exact same thing as before. So we see that 36, we're like kind of, when we're taking its factors and kind of taking those factors and kind of continually decomposing them, we see that underneath 36, we get a product of these prime numbers of 2, 2, 3, and 3. So what we're doing here right now is basically an example of a more general thing that we're about to get into called the fundamental theorem of arithmetic. So let's get into that, and we'll be able to see more what this is actually talking about. All right, so we have the fundamental theorem of arithmetic. I accidentally wrote at first the fundamental theorem of algebra, which is another really important topic in math, but it's something that we aren't quite ready for yet. But we'll get to it someday for sure. So the fundamental theorem of arithmetic says that for any whole number greater than 1, it can be factored completely into a unique product of prime numbers. Okay, so any whole number greater than 1, so that could be 2, 5, 3,000, right? It can be factored completely into a unique product of prime numbers. So we can take that number and split it up into prime numbers, kind of like what we did with 36, right? We took 36 and we found that it had some combination of prime numbers, namely 2, 2, 3, 3, that gave us 36 when we took their product. And furthermore, it says that this product is unique. All right, so let's give you another example. So if we took 50 we know is 2 times 25. And 25 we know is 5 times 5. So I was able to split 50 up into this product of prime numbers, right? 2 and 5 are prime numbers. And this is saying that it's unique, so there's no other combination of prime numbers that's going to give me 50. And if we tried this with other factors of 50s, for example, if we started with 5 times 10, we're going to end up with the same thing, right? 10 splits up into 5 times 2. So we get 2 5s and a 2, right? Just like we had over here. So we get the exact same product of prime numbers giving us 50. And the fundamental theorem of arithmetic says this is true for absolutely every single number greater than 1. So why not 1? Why do you think it's not including 1? Well, 1, as we've seen in previous videos, isn't prime. But we can't write 1 as the product of anything other than 1 times 1, right? That's the only pair of numbers, 1 and 1, that give us 1. But since 1 isn't prime, we see that 1 is basically just not going to be able to be factored into prime numbers because, well, 1 isn't prime. Every single other number will work. And in fact, if that number is prime, for example, 2, then we can just simply say, hey, that is a product of 2, where we're not multiplying with anything, but in a sense, this is like a one-fold product, you could say. If this was like a three-fold product, or 4 times 9, that'd be like a two-fold product. We could call this like a one-fold product, and basically say that 2 equals 2 does still fall into this situation, but because it's prime, basically it's already completely factored, right? As we saw in the last video, prime numbers, they can't really be divided down into smaller chunks. So we already have kind of the small chunk here when we have 2. All right, so now let's talk about why I say that primes are like the atoms of numbers. And maybe you already have a bit of an idea with this fundamental theorem of arithmetic. So what is an atom? Well, atoms are said to be like these fundamental building blocks of the universe, and atom actually originally came from a Greek word meaning indivisible, and that's because atoms were thought to be kind of like the smallest possible things in the universe. Now, if you know anything about atoms, you know they're made up of electrons, neutrons, and protons, which are technically smaller things that make up those atoms, right? But for the longest time, it was kind of thought that these like atoms are just as small as you can possibly get. But in any case, the idea is that everything in life, from this pen to my hand, is made up of combinations of atoms. And there's on the periodic table, there's 118 elements, but not all of them actually occur naturally. Some of them are like synthesized. But anyways, on the periodic table, there's a bunch of these atoms, and it's all of these combinations of atoms that give us everything that we see in the universe. So if you have something like water, for example, water is H2O. So what that means is you have an oxygen atom connected to 2 hydrogen atoms. And this is 1 molecule of water. So water is made out of this combination of 2 hydrogens and an oxygen. So similarly, if we take something like 50, which is 2 times 5 times 5, then what we're doing is we're saying 50 can be broken down into these small indivisible parts, just like H2O can be broken down into these indivisible atoms, which again, atoms aren't actually indivisible, but you get the analogy. And it's these indivisible numbers, these prime numbers, that make up absolutely everything. And just as a bit of terminology, when we take a number and we split it up into the prime numbers that multiply to give us that number, this is called the prime factorization of that number. So the prime factorization of 50 is 2 times 5 times 5. These are the atoms that make up 50. All right, perfect. So what we're going to do now is say, if we had a really big number, how can we actually go ahead and find the prime factorization of that number? I'm going to show you a nice reliable method to do that now. All right, so this example says find the prime factorization of 45. So 45 is a whole number bigger than 1, so the fundamental theorem of arithmetic tells us we're going to be able to split this up into the smaller pieces, into these indivisible prime numbers, such that when we put those together and multiply them, we're going to get 45 back. So now our goal here is to actually find what prime numbers will multiply to give us 45. And so this method is often referred to as factor trees. With this, you start with the number on the top, and the idea is you basically take off the smallest prime number you can that will divide into this. So we'll start with 2. 2 can't go into 45 since 45 is odd. But what about 3? Well, if we add the digits, 4 plus 5 gives us 9, which means, and 9 is a multiple of 3, so that means 45 is divisible by 3. So if we divide 45 by 3, we're going to basically pull off the 3, and 3 times what gives me 45? 3 times 15 gives me 45. So what I've done here is basically I've kind of started a new line where I wrote 3 and 5, which is just the factor pair that gives me 45. But the key part is one of the parts of this factor pair is a prime number. So 3 is going to be in our prime factorization. Now we go ahead and look at 15, and we do the same thing. So what prime number will multiply into 15? Well, 2 is not going to do it because 15 is odd, but 3 is, right? Since 3 times 5 gives us 15. And now we look, okay, 3 is prime, and 5 is actually also prime. So we're actually done now. So we get that the prime factorization of 45 is 3 times 3 times 5. All right. And really what this is a visualization of kind of how we were doing it with equations earlier, where we could say, okay, 45, that equals 3 times 15. And then we split 15 up into 3 times 5. So we keep the 3, and then 15 gets split up into 3 times 5. And we see that we get the same prime factorization. It's just this way is maybe a little more visual and might be more helpful for you. So let's try another example. Let's find the prime factorization of 42. All right. So we'll start with 42, and we will look at the smallest prime number that goes into it. Does 2 go into this? Yes, 2 goes into it because it's even, right? So we take off a 2. What's 42 divided by 2? It's 21. So that means we can split 42 up into the factors of 2 and 21, and 2 is prime, so we will be using that in our prime factorization, or basically the list of the indivisible numbers, or the atoms, you could say, that make up 42. Now we're going to do this for 21. So what can 21 go into that's prime? Well, does 2 go into 21? Nope. How about 3? Yeah, 3 goes into 21, right? 3 times 7 gives us 21. And would you look at that? We split 21 up into two prime numbers, 2, 3, and 7. So that means 42 here is going to be 2 times 3 times 7. This is the unique combination of prime numbers that when we multiply them is going to give us 42. All right, so let's try a bigger number now, and we'll see how this is still a very useful method. All right, so we're going to find the prime factorization of 1020. So we'll start with 1020, and then we're going to split it up into 2. What's 1020 divided by 2? Well, half of 1000 is 500, half of 20 is 10, so 10,020 divided by 2 will be 510. All right, so now we want to split up 510. Does 2 go into 510? It sure does, so that means that's a prime number that we're going to be able to chunk off here. And we now want to see, okay, what does 2 multiply to give us 510? Well, if you do maybe some long division, or you can do this in your head, you should get 255, because 2 times 250 is 500, and then 2 times 5 is 10, so 2 times 255 will give us 510. So now we got to deal with this 255. So 255, does 2 go into that? Well, it doesn't, because this is an odd number. How about 3? Well, yeah, 3 should go into this, because if we add the digits, 5 plus 5 plus 2, we get 12, which is a multiple of 3, which means that 3 has to divide it, 255. So we will get 3. Now, I'm not actually sure what 255 divided by 3 is off the top of my head, so we can just do a little division on the side here. And we get that 255 divided by 3 is, does 3 go into 2? Nope, so we have to move to the 25. Does 3 go into 25? It sure does, so we get 8, right, because 8 times 3 is 24. Subtract off the 24, we get 1, and then we bring down the 5, and now we see, okay, how many times does 3 go into 15? It goes into 15 5 times. So we subtract that off, and we get that 255 divided by 3 is 85. So we can split up 255 into 3 times 85, and that gives us our next piece of the prime puzzle to see what factors give us 1020. All right, so now we're on to 85. Does 2 go into here? No, it doesn't. How about 3? Well, 8 plus 5 is 13. So that's not going to work either, since 13 is not a multiple of 3. But now we want to see, okay, what is the next prime number? Well, it's not 4, because 4 is not prime, so we check 5, because 5 is the next biggest prime number. Does 5 go into 85? Well, sure it does, because 85 ends in a 5, right? So we know that 5 is going to be a factor of 85. And 5 times what gives us 85? Well, we could do it on the side again if we want. So We do 85 divided by 5. How many times does 5 go into 8? It goes in once. We subtract off 5. We get a 3. We bring down the 5, and we get 35. How many times does 5 go into 35? It goes in 17 times. So we get that 5 times 17 gives us 85. Now, 17 is also prime, right? Because, and you can check its factors to make sure, but yeah, 17 is a prime number. So that means 1020, its prime factorization, the unique combination of these indivisible numbers that give us 1020 is going to be 2 times 2 times 3 times 5 times 17. So I hope that made sense, and I just have one quick note to add. So ideally, you've seen exponents before, for example, 3 to the 4th power. And this power just means that you're writing out the number being multiplied by itself that many times. So 3 to the 4th power is the same as 3 times 3 times 3 times 3. Or 7 to the 3rd power is the same as 7 times 7 times 7. I multiply it by itself 3 times since I have 3 as the power here. All right, so for some prime factorizations, we get repeated elements, so it's often common to basically use exponents in the prime factorization. For example, 45, as we saw up here, was 3 times 3 times 5. But since we have 3 multiplying itself twice, we can say this is the same thing as 3 squared times 5. And this would maybe be a more compact way of writing the prime factorization of 45. Or 1020, we saw that was 2 times 2 times 3 times 5 times 17. So one way to write the prime factorization of this would be 2 squared times 3 times 5 times 17. And another number, let's say 200, the prime factorization of this, and you can check this yourself, is going to be 2 times 2 times 2 times 5 times 5. So what would be a more practical way, or a more condensed way using exponents of writing 200? Well, we could just do 200 is 2 cubed, since we have this prime factor of 2 3 times, times 5 squared, since we have this prime factor of 5 occurring 2 times in the product. So both ways are just as good, but this way is a little more compact because instead of writing a bunch of numbers in a list like that, we can kind of put all the copies of the number into this convenient exponent form. So I hope you found that video useful. And now we have a bit more of a good idea about why prime factors are so important. They're these indivisible things that every whole number is made up of when you actually break it down, just like everything in the universe is made up of these smaller atoms. And I think that similarity is quite a beautiful thing. But if you're still not convinced about, oh, I don't know, this prime factorization doesn't seem all that interesting, you're about to see some really useful tools in the upcoming videos that prime factorization makes use of, along with some really neat real-life examples. So I'm really excited to get into those, but until then, I'll see you in the next practice video, and have a good one, stay groovy, and I'll see you then.